Okay, this is section 6.6 for Calc survey, and this is a technique that I can't walk you through without demonstrating. So I'm going to demonstrate at least, hopefully, 5 examples for you to give you the general idea. And then the problems in the notes are just going to be extra ones for you to go through. These are problems from the notes, but I'm not doing them all. I just want to at least walk you through the process because it's a little bit confusing at first and it will take some serious practice on your part. All right, so this is called substitution. And the idea is this is not a basic integration problem back in section 6.2. You have to use a different technique to do this. Now, not technically. You could cube out that binomial, distribute the negative 8x, and then do the antiderivative of each term. But that's no fun. We have another way of doing this, and it's called substitution. So you're basically undoing chain rule. So you're looking for an inside function whose derivative is on the outside. Okay? And if you look carefully, see how you have a negative 4x squared? Well, 3 minus negative 4. If you do that derivative in your head, you get negative 8x, and that is on the outside. So what we're going to do is we're going to set u equal to the inside function. So 3 minus 4x squared, and then do the derivative. So du ends up being 3 turns into 0, and you get negative 8x dx. We write that as what we call a differential equation. Do we have a negative 8x dx on the outside? Yes, we do. So here's what we're going to do. We're now going to rewrite this integral in terms of u. So this inside gets replaced with a u, so we'll have u cubed. And then that negative 8x dx gets replaced with a du. And now we've created a much easier integral to solve. And now it's back to those basic integration rules. So this becomes, remember, you add 1 to the exponent, divide by the new exponent, and then your last step is to then replace that u with what it's equal to. So our answer ends up being 1/4 3 minus 4x to the 4th plus c. And if you remember, you can always check your answer. So if you were to do this derivative, you would use chain rule. So pull that 4 down in front, 4's cancel. Remember, the inside stays the same. Now it's raised to the 3rd power, which is right there, times the derivative of the inside. Ooh, I lost my squared. Sorry, there should be a squared there. I lost my squared. So when you go to do the derivative of the inside, there's that negative 8x. So it works. Okay. So that's one example. All right, let's try this one. So definitely not one of your basic integration rules. So look for an inside function whose derivative is on the outside. So, and with polynomials, x to the 4th, I need an x cubed. Well, yeah, I have an x cubed up here in the numerator. So let's make u 1 plus x to the 4th. So then without looking at your integral, do this derivative. So du becomes, and guys, technically this is du dx. You're doing the derivative with respect to x. So you'll get 1's just 0, you get 4x cubed, and all I'm doing is multiplying over that dx, just to make it look like what we have over here. Du, just like dx, will always be in the numerator. And do we have a 4x cubed dx? Almost. We almost have that. We have a 2. Well, we can easily fix that. What if we just did a 2 in the numerator, and then to make it legal, we have to put a 1/2 out in front? That is perfectly legal. We technically multiplied by 1, but now we have what we need. So we're going to have 1/2 times the integral. Now that entire numerator, that 4x cubed dx, is what gets turned into a du. And we'll have a 1 over the square root of u left. And now we're right back into those basic integration rules. This is really 1/2 times the integral of u to the negative 1/2 du. And now you can use the power rule. You can add 1 to the exponent, and then whenever it's a fraction, you flip and multiply because you're dividing by the new exponent. So when you flip and multiply, you'll get a 2. Those 2's, of course, cancel, but you never leave u in your answer. You then need to replace u with that binomial. So with the 2's cancel, so we're left with 1 plus x to the 4th raised to the 1/2 plus c, and that's your answer. Right? And again, you can mentally go through and do the derivative real fast to make sure you get back what you started with. Okay, now here's an interesting example. So in the last two examples, we talked about looking for the inside function whose derivative is on the outside. Well, in this case, and in those two examples, there was a nice parentheses, or in the previous example, there was a square root. So we need to take the entire thing under the square root. So in this case, well, there's no parentheses, but if you think about it, that entire denominator down there, if we make that the u, then we do the derivative, we'll end up with, you kind of have to think a couple of steps ahead. Well, we can make this into 1 over u, and you know how to do that antiderivative. So when presented with a fraction like this, you'll want to maybe attempt to make the entire denominator your u. So that's what we're going to try. And guys, I've done lots and lots and lots of these problems, so I'm always thinking a couple steps ahead. You guys might get into the scenario where you've picked a u and it doesn't work. You might need to start over and try again. That's why it's so important to make sure you're doing your homework on these problems. All right, so I made the entire denominator my u. So now do the derivative. So when you do this derivative, remember, it's this 2 is 0. You get negative e to the 3x times the derivative of the exponent, which is 3. And then dx, if you want to put that. Now, do I have a negative 3 e to the 3x in the numerator? Not quite. But that can be fixed. We can easily, we're missing the negative 3 part, so we can easily put a negative 3 here, but to make it legal, we have to put a negative 1/3 out in front. We can only multiply something by positive 1. All right, so I think we're ready. So now we have negative 1/3 times the integral. Now we're going to write this all in terms of u. There cannot be any x's left. So this entire numerator gets replaced with a du. And we'll have 1 over, then that entire denominator gets replaced with u. And guys, if you just make e to the 3x your u, when you get down here, you'll have 1 over 2 minus u, and then you're right back in the same scenario you started with. So that's why it's advantageous to make the entire denominator u. Because now the antiderivative is really simple. 1 over x, remember, is natural log of the absolute value of x. So in this case, we'll have negative 1/3 times natural log of the absolute value of u. But then never leave u in your answer. Replace u with what it's equal to. So negative 1/3 natural log of the absolute value of 2 minus e to the 3x plus c. That's your answer. All right. All right, here's another fun little example. So when using substitution, you're looking for an inside function whose derivative is on the outside. And you do have parentheses here. Just because it's in parentheses doesn't make that our inside function necessarily. But it kind of is a little hint that potentially that might be it. So when I see natural log of x, think through the derivative. The derivative is 1 over x. Do I have a 1 over x on the outside? Yes, I do. I have a 1 over x. So, yeah, let's try it. So let's make u natural log of x. So then the derivative, du, is going to be 1 over x dx, and I have a 1 over x dx on the outside. So now let's rewrite this. So natural log of x is the u, so you get u squared times, and then the 1 over x dx is what gets replaced with a du. And then always ask yourself, did you improve your situation? You should always get it down to where it's just another basic antiderivative. So, and it is, that's just the power rule. So we add 1 to the exponent, divide by the new, and then your last step is to replace that u with natural log of x. So be careful how you write this. Natural log of x all cubed plus c. Okay, so speaking of parentheses, here's an interesting one. So again, you're looking for an inside function whose derivative is on the outside. And your ultimate goal is to rewrite the integral in terms of u so you can actually solve the integral. Well, you say, oh, parentheses, that's going to be the u. But when you go to do du, you get 4. And that does not solve the issue of your exponent here. Okay, well, you have a polynomial function, x squared. I know that's going to turn into, when you do the derivative, it becomes degree 1. Ooh, I have a degree 1 function here. So that actually, the exponent is looking like that's going to be a better option to be the u. So make the entire exponent u. So x squared plus x minus 3. So then du becomes 2x plus 1 dx, if you want to write that. This is just scratch work over here. So if you don't write the dx, that's okay. Now, do I have a 2x plus 1 dx? Ooh, I'm close. What if I rewrote this? What if I factored out a 2? So that would be 2x plus 1 e to the x squared plus x minus 3 dx. Ooh, now I have it. And that 2 is just a scalar, so I could easily just move that in front of the integral. So I think we're in business. You need to be able to rewrite the entire integral in terms of u. And I think we're good to go. So we'll have 2 out here in front, the integral. Now this 2x plus 1 dx is what's getting replaced with the du. And we'll have e to that entire polynomial, it's what's getting replaced with u. And that looks much, much better. Now we're back to a basic antiderivative. E is just e, so 2e to the u, but then you need to replace that u with that polynomial. So you get 2e to the x squared plus x minus 3 plus c. And that's your answer. Hopefully you can see that. Okay, so hopefully you found those little examples helpful. Now, if you scroll through here, you'll recognize some of them that I just showed you, but it's going to be really good for you to go back and mentally think through these extra examples. I use W in the notes. It doesn't matter if you use U or W. That's perfectly fine. There's a reason in the next section I picked W, because we're going to use a different kind of U when we do integration by parts in the next section, but whatever you feel comfortable with, U or W, it does not matter. But there are some good examples in here for you to go through and practice. DW is always in the numerator, always. You know you've done something wrong when you're using substitution and the DW or the DU, whichever you're using, happens to be in the denominator, something went wrong. All right, now down here at the bottom, these are just some extra, just if you want a little bit of a challenge. So I threw some Calc AB problems in here for you that are extra fun. This is one where it's not so obvious that you want to use substitution. You could even use long division if you want to do this problem. We're going to start getting into problems that you have multiple ways of solving. So if you try using substitution, or if you want to multiply out the binomial, maybe it's cubed and you'd rather go that route, that's perfectly fine. We're going to start doing problems where there's more than one way to solve. Okay. And then this last section is changing the bounds. So when you do substitution, you need to make sure, so in this case, you set your W equal to 2x minus 2. dW is 2 dx. We had to create that too. When you go to write the new integral, you cannot keep the bounds. You have to change them to in terms of W. So plug the 2 into this 2x minus 2. That's the new lower bound. And then plug 4 in, you get a new upper bound of 6. So when you do the antiderivative, the beauty is now you can just plug those numbers into W and you get your answer. So you don't pull X back into the problem. But we will definitely do some of these in class. please do your homework. Let me know if you have any questions.